So I'm trying to there's a way to
Okay, everyone, we're gonna start our special seminar today. We're very happy to have John Sorce, who's visiting us from MIT. He'll tell us here about some recent work on relating the bulk causal structure to sort of entanglement properties in the field theory.
Excellent. All right, thank you, Edward, for the introduction. Thank you, everyone, for having me. I will be here for a while. I'm here until the 22nd, so I'm happy to chat with people about anything I discussed today or anything else. What I'm going to be telling you about is a set of ideas that I've been developing in large part through discussions with Alex May and also through collaborations with Alex, Jeff Pennington, and Benny Yoshida. These are sort of the three main papers that you can look at if you want to get a better sense of what we've been thinking about. But the punchline, if you want, a guidepost going forward, is that I'm going to be telling you about a way of applying a certain kind of quantum information reasoning to holographic quantum gravity that will reveal a couple of interesting things. One of the things that it's going to reveal is a relationship between causality and entanglement in any consistent holographic theory of quantum gravity. And the other thing that it's going to reveal is actually sort of a reverse implication where the ways that we reason about gravity will feed back into new insights about quantum information theory. And hopefully we'll have time to discuss both directions of this implication and what they can teach us. So this is a pretty broad group, I know. I'm going to start with a short discussion of some classic causal puzzles in holography. I'll give the perspective that I'm going to be taking on holographic quantum gravity in this talk, and I'll review some of the puzzles that arise about causality from the perspective of quantum field theory. But then, in the second part, I'm going to move away from the quantum field theory way of thinking, and I'm going to introduce an information-theoretic way of reasoning about causality and quantum gravity that will give us a new handle on some interesting new physics. Then in the main part of the talk, I will give you some very precise conjectures about relationships between causality and entanglement in ADS-3 theories of quantum gravity. And I will give multiple independent arguments for those conjectures that follow from sort of completely independent lines of reasoning in a way of trying to convince you that these things are true and meaningful. And finally, if we have time, I'm going to tell you about how you can take all of the reasoning that we develop in part 3 of the talk and remove the gravity from it and just come up with some conjectures about quantum information theory that you can then prove using just the tools of quantum information theory. So it's sort of an interesting way that the gravity reasoning feeds back into the information theory literature. All right. So this is a talk about holographic quantum gravity. And the viewpoint you should have in mind is this old conjecture that any consistent d-dimensional theory of quantum gravity admits a dual description as a d-1 dimensional quantum field theory. Now, I'm going to take that conjecture pretty abstractly in this talk. There are many concrete realizations that I know many people in this room have worked on coming from string theory, these ADS-5 systems, these ADS-4 systems, the ADS-3 system, and the recent Jakiv-Teitelbaum correspondence. But what all of these features have in common is that while the specific string theory descriptions that you look at tell you some interesting facts about the microscopic UV physics of the theory, all of these features, when you sort of wash them out and look at them at some very coarse level, share a fundamental set of properties that we can abstract away into what we might call the axioms of ADS-CFT. And what these axioms concern are ways that correlation functions in one theory map to correlation functions in the other, right? How correlation functions in your d-dimensional theory of quantum gravity map to correlation functions in a d-1 dimensional quantum field theory. And these axioms actually have, they can be argued for without working in any particular microscopic model through some natural assumptions about how the path integrals of the theories are related and then formal manipulations associated with that.
Can I ask, so,
yeah.
I mean, if you go back, here, I mean, a theory of quantum gravity, I mean, it might look very far from, quote, gravity, if we're talking about like a free quantum field theory, for instance, just to
that's
put
right.
a
That's
fine
right.
point on
That's
that.
right.
So it seems like if you have a conjecture that is true at this level of generality, it must be almost kinematic in nature.
Yes. I think that's fine. I think in the next slide, I will specify and take a limit where it stops being just a trivial little kinematic statement. Okay? But I think it's, it's a fair point. I'm always going to have in mind some strong coupling large N limit implicitly.
Would these results also hold for like the very stringy limits in holography?
No. I'm going to be talking about classical limits, and that'll become clear when I talk about the specific conjectures I have in mind. So it's pretty easy to envision how the holographic dictionary should work at sort of the abstract level in an asymptotically anti-de Sitter theory of quantum gravity. And the reason for this is just that the formal boundary of an asymptotically anti-de Sitter spacetime is time-like. What that means is that it's very natural to guess that if there is a quantum field theory dual description of the theory, it ought to be realizable as some quantum field theory on that time-like background. Okay? Under this assumption, we end up with a very natural conjecture for how the two theories should be related, which is just that my quantum field theory is going to have some set of operators. And if I try to compute correlation functions of any of those operators, it's always going to be possible to map each field theory operator to some asymptotic quantum gravity operator such that the correlation functions match. Now, this is, I think, getting to Clay's question. This expression is pretty confusing. What I might mean about the correlation functions of some asymptotic observables in a quantum gravity theory. And indeed, the cases in which we're going to be able to make sense of this expression are the cases where we're working in some theory that is, in an appropriate limit where it's approximately described by Einstein gravity. Okay. So the core, idea going forward is that if we have a theory of quantum gravity that describes semi-classical physics, perhaps general relativity plus some other fields, potentially those fields are quantum, then in any state of the quantum gravity theory, well, I should say probably, states of a semi-classical quantum gravity theory describe configurations of the gravitational degrees of freedom. So in particular, there should be states in that theory that describe spacetimes, and different spacetimes should correspond to different states. So if we are in a coherent state of the quantum gravity theory, by which I mean a coherent state of the gravitational field, a state in the quantum gravity theory that describes a spacetime, potentially with some quantum fields propagating on that spacetime, then the right-hand side of this inequality should, in principle, be computable as a quantum field theory calculation in a fixed spacetime background. There are plenty of caveats to this. You have to worry about what if these observables have very high energy, maybe then there's a back reaction problem you need to worry about. I shouldn't trust this kind of effective field theory calculation where I treat this quantum gravity calculation as a QFT and curved spacetime calculation. But there are definitely regimes where correlation functions in quantum gravity should be able to be computed as QFT and curved spacetime correlation functions, up to certain non-classical corrections. Okay, so let's just take this equation seriously for a moment. Let's imagine there exists a theory of quantum gravity which contains states corresponding to spacetimes, and there exist correlation functions in that theory that can be computed using QFT and curved spacetime, and that those things correspond to correlation functions in some holographic dual. Immediately, we arrive at a puzzle, and this is a puzzle that has been discussed by many, many authors, which is that in a quantum field theory, correlation functions are sensitive to causal structure. Strictly speaking, I mean an interacting quantum field theory. I think the thing I'm describing doesn't actually happen in free theories. But if I have an interacting quantum field theory, then it's just generally true that 4-point functions of operators develop singularities when those operators are placed in such a way that they have some non-trivial S-matrix element. Okay? This is a general feature of interacting theories. If I take sort of two observables and I insert them in the past and two observables and I insert them in the future, and my space-time causal structure is in such a way that particles beginning in at those locations could scatter, this causes a singularity in the 4-point function. If you're not too familiar with this kind of thing, it's okay, just take it for granted.
That singularity would be a 1/n effect.
Absolutely.
It would go away with
Absolutely.
1/n corrections, right?
Absolutely, yeah, that's right.
Okay.
So the thing that's interesting, the thing that's interesting about this observation that quantum field theory correlation functions are sensitive to causal structure is that if I take holography seriously, then I have to deal with the fact that the two sides of the duality can have inconsistent causal structures, or rather they can have different causal structures, right? In particular, in my quantum field theory, I'm doing I'm studying a quantum field theory on some fixed background. So its causal structure is just an intrinsic property of the theory. But if I'm talking about quantum gravity, then different states of the theory correspond to different spacetimes, and as a result, the causal structure is state dependent. And what that means is that this dictionary that I described earlier, where quantum field theory correlation functions map to quantum gravity correlation functions, can pose some puzzles. Because you can you can look at spacetimes and configurations of boundary points for which the causal structure in the bulk, the causal structure in the quantum gravity theory, gives rise to some apparent singularities in correlation functions that are not visible from the perspective of the boundary theory. Now, I'll give a classic example that I think will sort of make this very clear. Consider the ADS3 vacuum. And I'm going to consider 2 points on an early time slice and 2 points on a late time slice. These early time points are antipodal on the early circle, and these late time points are also antipodal on the late time circle, but they're rotated 90 degrees relative to one another. And I'm picking units where the perimeter of the boundary circle is 2 pi. If I separate these 2 time slices by boundary time pi, well, it takes a light-like signal from the boundary time pi over 2 to get the center of the bulk. And what that means is that signals starting at these 2 points could come into the center of the bulk and meet, scatter, and then separate to the output points 03 and 04. No such thing is possible in the boundary spacetime of the cylinder. There's just no way that if I restrict myself to the boundary, causal signals from these points could meet and then scatter to both of these output points. The reason for that essentially being that signals starting from these 2 points will have to meet either on the front of the cylinder or the back of the cylinder. And once they do that, they won't be able to reach both of the outputs. Okay. The reason this is a puzzle is that if I'm just using sort of the rules of quantum field theory and I'm just thinking about the singularity structure that I described above, consistency of this holographic dictionary would seem to require that the bulk correlation function has an obvious singularity, whereas the boundary correlation function doesn't seem to have any natural reason for a singularity to appear. Okay, this is a classic puzzle. I'm not going to talk about it at all after this slide, so if it's not your preferred way of thinking about things, feel free to just forget it. But I bring this up because this is a way that many authors have tried to talk about how consistency of a putative ADS-CFT dictionary restricts the structure of quantum field theories that might be holographic. If I have a quantum field theory and I want to ask, can this quantum field theory have a gravitational dual? Can it have a semi-classical gravitational dual? Well, there's going to need to be some physics in that field theory that is going to be able to account for these kinds of singularities that appear when I look into the bulk description. Right.
So are you assuming the
Yeah.
degrees of freedom on the boundary are massless? Or?
Take pi plus epsilon if they're not. You'll end up with the same problem. Okay. So I bring this up only to say that there is a history of looking at these kinds of things where causal structures in the interior of a spacetime must put constraints on the structure of the boundary quantum field theory state if this kind of dictionary is to make sense. So that's the first part of the talk, reviewing these sort of classic ways of thinking about causality and holographic quantum gravity. What I'm going to do going forward is I'm going to introduce a completely new way of thinking about these puzzles that uses the language of quantum information theory. And it has been my experience that these ideas can be a little confusing at first. So, I've iterated on this explanation many times, but if you do find yourself confused, please interrupt and ask me a question. So let's back away from gravity for a moment, and let me just tell you some facts about quantum information theory. There's a catchphrase I'd like you to remember, which is that causal structure can be used as a resource for information processing. This statement might seem kind of oblique at first. When I explain it, it's going to be completely trivial. What I mean by this is that suppose Well, okay, it's going to be easiest to understand what I mean by this if I first introduce the idea of a quantum task. Now, a quantum task is an information processing challenge that is posed in spacetime. So imagine I have two observers, Alice and Bob, and Alice and Bob are handed some shared state, rho AB. Some third party gives them this state at particular spacetime locations, and then says, okay, I'm going to name for you a certain quantum operation, some general quantum operation E, that I want you to apply to that state. And then I want you to return the output of that operation to two other spacetime points. So I've sketched that very roughly in this picture. Alice and Bob start at two spacetime points. There are some other spacetime points specified in the future. They are given some state rho, and they're asked to apply a quantum operation and return the outputs to some other spacetime location. So that's a task that Alice and Bob might be asked to do. It's a kind of information processing challenge. And what I mean when I say that causal structure can be used as a resource for information processing is that if Alice and Bob live in a spacetime where it's possible for them to meet locally in between these two sets of spacetime points that have been specified, then they can use that meeting point to perform this quantum task. Yeah.
So Alice and Bob can only do local.
Alice and Bob are local people, they have local operations. Yeah, that's right. Yeah. Right. It can be, that's right. It can be Edward and John, if you and I want to meet up very quickly and do an operation and then run to opposite corners of the room by a certain time. That's the sort of task we might be asked to do. Okay? So if they live in a space-time where they have a region where they can meet like this, then that's something they can use to do information processing. I think this is, more or less a trivial statement. The non-trivial statement is a very interesting theorem from quantum information theory, which is that causal structure, if we think of sort of causal meeting points as a resource for information processing, those meeting points can always be replaced by an appropriate entanglement resource. So this is a theorem due to Begy and Koenig. Now, before I read the theorem, I want you to sort of stare at this diagram for a second, and let's actually compare it with the diagram on the previous slide. So in the diagram on the previous slide, I had Alice and Bob coming together to a central location and then separated. Now I'm going to imagine that Alice and Bob are still able to send whatever they like to the output points from the original problem, but they're never allowed to meet locally. There are a couple of ways you can imagine this happening. This is the kind of thing that happens on the cylinder, the cylindrical spacetime that I sketched earlier. It's also, you could imagine that maybe there is some spacetime region where Alice and Bob could in principle meet, but there's some adversarial enforcer hanging out in that spacetime region who's going to stop them from ever interacting. Okay? So this is a new kind of challenge that Alice and Bob might have to undergo. And there's this very interesting theorem, which is that no matter what the quantum operation is that they've been asked to perform, it can be approximated non-locally by consuming a maximally entangled state. And the accuracy of the approximation becomes perfect, and the limit as the dimension of the state goes to infinity. So what this means is that in addition to being given some starting state, rho, that they're asked to act upon, Alice and Bob are given some resource, some huge number of bell pairs that they share, each holds half of these bell pairs. And there exists a protocol that uses those bell pairs in order to approximate this operation non-locally. I am not going to tell you what the protocol is. It's sort of an advanced version of quantum teleportation that uses some special fancy subroutines. Okay? So I introduced this theorem as a motivation for a way of thinking about information processing, which is that when you don't have causal structure, you can make up for it in using entanglement. Now, the way this is ultimately going to be applied to holography is in a scenario like this, where one side of the duality has causal structure and the other doesn't, and we're going to want to reason that the side of the duality with weaker causal structure has to make up for it using entanglement. Yes?
What kind of bounds are there on the error to this approximation, and do they depend on whatever notion of causal structure there would be?
Yeah, let's stick to the 2-to-2 case where it's very easy to describe. The Begy-Koenig theorem is a proof of concept. It is an example of a protocol that you could use. It's a very inefficient protocol.
I see.
The dimension of the state that you need to consume is exponential in the accuracy, or exponential in 1 minus the accuracy, or whatever the appropriate,
I see.
or 1 over the accuracy, whatever the appropriate measure is. So as you want to get your accuracy better and better, you need to use an exponentially greater number of
So
vectors.
there's no fundamental bound on how
Oh.
minimum the error can be.
Yeah, there is some fundamental bound. Well, actually, this next theorem will answer that, so maybe when we get to that.
Gotcha.
There was another question?
No, I was just going to ask, like, is it inverse Pauli, but you just said
Yeah,
it's
yeah,
inverse
okay.
exponential.
So, what I'm going to tell you now is a sort of converse to this theorem. It's not an exact converse, but it's an implication that goes in the other direction. I told you that given, I can replace causal structure with entanglement. Now I'm going to tell you a theorem that says there are certain cases where if I know that I can replace causal structure, I know that I have to have entanglement. All right? So it's sort of a converse. It says, sufficient versus necessary exchange. Now, this theorem, sort of a very early version of it was proved in this interesting work by Thomas Michel et al., but the version that I'm stating here was proved by Alex May and Jeff Pennington and myself in one of our papers. So what we can do is we can construct specific families of quantum tasks for which we can prove necessity of entanglement for non-local implementation, right? The top theorem says there's a sufficiency of entanglement for non-local implementation. So here's how this works. There's going to be a family of tasks. I should have written this. I'll write Tn here. So Tn is a task that is indexed by some integer n, okay? And I can construct these family of tasks for which it's provable that non-local implementation requires a resource state with a mutual information that scales extensively in this parameter n as n goes to infinity, okay? In particular, you can prove
What's the
that
definition of a task?
a task is this thing that I described on the previous. Alice and Bob are given a state and they're asked to act with a channel in that state. And they're asked to return that state to a final location. And at the end, some third party can perform a generalized measurement to determine whether or not they've
So
succeeded.
there's no restriction on the kind of function that epsilon can be there?
So it's a quantum channel. So that means it's the most general thing that you could do to a quantum state using a quantum computer. It means you can add in a reference, you can add in an environment, act with a unitary, and then trace out the environment. Yeah. You could think of it as a unitary operation if you want. In fact, the task that we use, this Tn, does use a unitary, not a quantum channel. Yes.
Is this lower bound tight, the bound from your theorem, the omega n?
But we don't know. I don't have anything to say about that. All I know is that you can prove that there is a lower bound. So the point is that I can exist a family of tasks, and if I can tell you, there exists a family of tasks, and I can tell you, if this family of tasks is possible, if I have some other way of arguing that this family of tasks can be done, or if I see that it has been done non-locally, then I say, well, their resource state had to have had a mutual information that scaled with the number of qubits, because otherwise they just wouldn't have been able to do this. And this is actually, you can prove this bound. The bound looks like the mutual information is bigger than or equal to n over 2 plus some things that are subleading in the large n limit. So it's a very, very precise bound that you can write down. Incidentally, if you're curious about the history, what Thomas Michel et al. Did was they constructed a family of tasks for which they could prove that the task could not be done if the mutual information is 0. The May et al. Improvement is to show that there's a family of tasks for which you actually have a lower bound on the required mutual information.
What is omega?
Omega, this is big omega notation. So what this means is, so big O notation would mean that I could scale as less than or equal to n. Big omega notation means that I needs to scale as at least n, right? So I could scale as n squared, n cubed, but it can't scale as anything smaller than linearly in n.
Okay.
Okay. Maybe another important fact. There are 2 important facts about this family of tasks that will come up in a slide or 2. One is that this number n is the number of qubits involved in the task. So it's the number of input qubits, or like the dimension of the input system, right? And the other fact is that the actual quantum channel that they're being asked to do is simple. It's a simple quantum channel, and what I mean by that is that if Alice and Bob had a quantum computer and they were trying to implement this channel on their quantum computer, they would be able to do it in a circuit that only has like 3 steps. The number of steps wouldn't scale with the size of the system. That'll become important in a moment. And I'll revisit it. I won't expect you to remember that. Okay. So here's the broad proposal. And you know, this is a very vague statement, but I want to emphasize, and I'll give you a very precise statement in the next slide, but I want to tell you what the idea of this program is. And the idea of this program is that quantum information theory tells us that causally local information processing tasks have a relationship with causally non-local, but entanglement assisted quantum information processing tasks. So let's view that in light of this observation we made earlier, that the causal structure of a spacetime can be richer than the causal structure of its boundary, right? So the broad proposal is that if the ADS-CFT dictionary is to be consistent, then causal features of bulk spacetimes should be reflected in the entanglement structure of the boundary state. Well, which causal features? The ones that can be used for information processing. Which entanglement structures? The ones that can be used to replace those causal resources. Yeah.
In this theorem, does it matter in any sense whether Alice and Bob were, say, 10 feet away or sort of 2 light years away?
No, the only thing
So if
that,
there was any non-locality in the bulk, even at small scales,
yeah, this is a very important and interesting question. I'm using sort of a cartoon picture where like Alice and Bob, or you know, Alice is some agent here, Bob is some agent here. Bob can send one-way communication to some output, Alice can send one-way communication to some output, but I'm not thinking too deeply about things like, well, is Alice spread out a little bit? Is Bob spread out a little bit? Is there perhaps some, the thing you're thinking about is, you know, bulk entanglement and whether that can be used or things like that. My answer for you that will maybe satisfy you is that everything, if we're thinking about holography, I'm going to be making statements that are like scaling with n in the large n limit, and bulk entanglement does not scale with n in the large n limit, so it's kind of going to decouple from the problem. But I think probably anything more precise would be better left for after the talk. Okay. All right. That's all of these first 2 sections. Now what I'd like to do is tell you some precise conjectures about ADS-3 quantum gravity, if there exists, you know, I mean, this should work for example, for the D1, D5 system, but it should work for any ADS-3 theory of quantum gravity. Let's return to our 4-point example in the ADS-3 vacuum. Now, I've told you that I can arrange a situation in the bulk where I have 2 early time points and 2 late time points with the property that it's possible for causal signals from the early time points to meet in the bulk and scatter to the late time points. I'm going to start giving these points names. The early time points will be C1 and C2, and the late time points will be R1 and R2. And what I've done here is I've drawn the boundary spacetime, which has the topology of a cylinder, and I've unwrapped it. So let's identify the right and left sides. And what I've done is I've sketched the points C1, C2, R1, and R2, and I've drawn their light cones. So ignore the green shaded regions for a moment and ignore the labels A and B. The thing I want you to notice is that, as I said at the beginning of this talk, this 2-to-2 causal interaction that's possible in the left side is not possible in the right side. If I look at all the points that are in the future of both C1 and C2, well, there are some of those that are in the past of R2, that's this diamond up here. And there are some that are in the past of R1, that's this diamond over here. But there are none that are in the past of both. Now let's think about this from the language of information processing. Suppose Alice and Bob are 2 agents who start at the boundary of this spacetime. And suppose we take seriously the ADS-CFT dictionary. Now Alice and Bob, these 2 agents, are given a quantum task that they're asked to perform. And they're asked to perform this quantum task starting at C1 and C2 and ending at R1, R2. Now, if Alice and Bob jump into the bulk, if they go into the bulk theory, then they can perform this task locally, right? They can meet up, perform a quantum operation, and separate. However, if Alice and Bob cannot go into the bulk theory, if they're restricted to the boundary theory, then they can do no such thing. So if we want to take the duality seriously, we need to find some other way for Alice and Bob to be able to do this information processing task using only the resources visible on the boundary theory, right? Now, yeah, Dane.
So I guess my naive intuition would be that something in the deep bulk would be some, very delocalized process on the boundary.
That's right.
So,
That's right.
I mean, what's preventing, A and B from producing some, they insert some operators, some stuff propagates forward within the light cone, some very delocalized interaction happens, and then, the results of that propagate forward to R1 and R2.
That's exactly what will happen.
Okay.
Right? So if that's exactly what will happen, right? So good. This is a good way of thinking about it if it's your, preferred way of thinking about the problem. If I sort of arrange an initial conditions such that this operation will be implemented in the bulk, you're right that on the boundary that would look like some highly non-local thing. But it will still happen on the boundary, right? And so the question we want to ask is what constraints can we put on the boundary state using the fact that this operation happens or can happen due to time evolution on the boundary. Okay? Edward.
These O's are, even in the bulk, you're starting extremely close to the boundary, so they're still fairly localized on the boundary.
Yeah, that's right. But as
That's
they go,
a 4-point function of fairly localized operators.
yeah, but when we think about a unitary process that causes a quantum operation to
following
happen in the
through.
bulk, that's right. They'll start localized here and here, but they will delocalize as it happens. Right. But let's return, I think that way of thinking, well, the technically stronger way of thinking is going to be less intuitively clear. So let's stick with this, Alice and Bob are trying to do a task way of thinking. Let's ask, if Alice and Bob stay on the boundary space-time, what can they do? They're trying to do a task that starts at C1 and C2 and ends at R1 and R2. Well, the only plausible thing that they could do, Alice can act within this diamond V1, and Bob can act within this diamond V2. How are those defined? I'll introduce some notation here. J plus of a point denotes the causal future of that point. This hat over J means that I'm talking about the boundary notion of causality. So I have some point, I look at its future restricted to the boundary spacetime. Okay. Now, V1 is the set of all boundary points that are in the future of C1, which is the point where Alice starts, but still in the past of both R1 and R2. Why is this a natural region to consider? Well, if Alice is some boundary agent who has to do some set of quantum operations that the data from which needs to end up at R1 and R2, well, she had better do all of her operations while still within the past of R1 and R2 so that she can send her outputs to those locations, right? So these are this is the natural place where Alice should be able to act in order to try to do a quantum task in the boundary space-time, and this is where Bob should be able to act. Well, what can they do in those regions? They are living in a space-time that has some conformal field theory state on it. So the kinds of things they can do are they can couple to the conformal field theory state within that region and interact with it. In particular, they can use the conformal field theory state restricted to this region as a resource, like the maximally entangled resource that we were talking about a couple slides ago. So here's a precise conjecture. Suppose I have a holographic theory of, a 3D, 2D holographic theory of quantum gravity in a semi-classical limit. And I have some state psi, which is a 2D quantum field theory state that describes an asymptotically ADS3 spacetime. I'm sorry, that's cut off. That says asymptotically ADS3. Now I'm going to fix points C1, C2, R1, and R2 that have the same kind of properties, causal properties as shown in this example. So here I'm introducing some new notation. When I write J hat of C1, C2, arrow, R1, R2, what I mean is the set of all boundary points that are in the future of both
psi is the vacuum?
No, it need not be the vacuum anymore. It could be the vacuum. In the previous example, it was the vacuum, but now it could be BTZ, it could be, any space-time state you like.
Any state?
I want it to be anything that has a classical dual. I don't want the dual to have a lot of strings in it.
I know, but then it doesn't, I'm trying to understand if there's a conjecture that I can test here in two-dimensional quantum field theory. And so far, because of that restriction on psi, I don't see how to test it.
What restriction on psi?
You said that psi can't be any state. It has to be a state that has some nice dual.
Yeah, that's
I
right.
don't really know what those states are if I'm just a 2D QFT person.
We'll start with the vacuum. That's one
Okay.
that will have a nice dual, right?
we can do the vacuum.
And you can feel pretty good that some high energy eigenstate is going to look something like a black hole microstate. I feel less comfortable with that, but still sort of okay about it.
Well, the spirit in which I'm trying to understand this conjecture is as something I can apply to 2D quantum field theories to test if they're holographic,
Yeah.
at least in the large C limit.
Yeah.
So
Okay, so let's
for that-
start with the vacuum, right?
Yeah,
I mean,
so for that input, it would be nice to not refer to the bulk already.
good. So pick the vacuum. The vacuum is one where you know everything, right?
But is this a theorem then that is just true as a consequence of conformal symmetry?
No, in the same sense that the emergence of the singularity in the conformal field theory only appears when you have this large gap, etc. Right? This is the HPPS.
But if I just put the constraints, the like Hartmann-Keller-Stoica constraints on the spectrum, will I derive this theorem?
It's a great question. I don't know. It'd be very interesting to find out.
Asking if this is like a sort of stronger, more like fine meshed.
I'm trying to understand how much teeth this constraint on the boundary has. Like,
See, that's hard, right? Because if you think, it makes me think about, okay, actually, in light of time, I think I should probably not get distracted by this, but we can talk after. Okay, so this notation that I've introduced, maybe I should write it explicitly. I have j hat c1, c2, arrow r1, r2 is j hat plus of c1, intersect j hat plus of c2, intersect j hat minus of r1, intersect j hat minus of r2. Okay? So remember, j denotes boundary causality. So this is the set of all points that are in the future of both c1 and c2, and the past of both r1 and r2. Okay? So I'm picking 4 points such that that region is empty, which means no 2-to-2 causal process is possible in the boundary space. Now j without a hat is going to denote the bulk causality. And the assumption I'm going to make is that the corresponding set, this 2-to-2 set, is non-empty in the boundary. Now if you're curious about this little circle that I've added above the set here, that's not a typo. What I really mean is that I want this region to have a non-empty interior. I want there to at least be some open set of points with this property, but that's sort of a technical condition about not wanting to get stuck on degenerate cases. You know, I want Alice and Bob to have a real space-time region they can act in the bulk, not just some measure zero set of points. Okay. So the conjecture is going to be that if we look at these V1 and V2 regions that I defined over here, then the mutual information between those regions is going to have to scale extensively in the holographic parameter. This ADS radius over G Newton, which is the dimensionless parameter that goes to infinity in the holographic limit. Clay, if you prefer, is the central charge of the field theory.
Well, I'm trying, like the mutual information, is that a 4-point function of twist operators?
It is a 4-point function of twist operators.
And then if I assumed it was dominated by the vacuum, I would probably derive that OC contribution.
Yeah, the thing I worry about a little bit is, right, I mean, let's talk about this after. You want to think about the Hartmann calculation where you do the OP fusion for large intervals versus small intervals, and something like this might come out. I think that's probably true, but I haven't thought about it. Okay, so the conditions of this conjecture are very natural. They're sort of the ones that I described earlier as giving me some information processing task that can happen in the bulk and not the boundary. I've described that, you know, a way of reasoning that suggests that whenever something like this happens, we should have entanglement. So why is this my particular conjecture? Well, I think that the entanglement resource ought to be associated to some correlations between V1 and V2, because those are the resources that boundary Alice and boundary Bob could use. Why am I conjecturing that this thing has to scale like the holographic parameter? Well, the most naive thing is that if it doesn't scale like the holographic parameter, then this is sort of a pointless conjecture. Because any two regions in any quantum field theory are going to have some non-zero mutual information. The interesting thing is if I can argue that that mutual information scales parametrically in a semi-classical limit.
Like, how did you know it was like linear? Why isn't it logarithmic, for example?
Oh, because of the Ryu-Takayanagi formula, entropies go like 1 over G Newton. Okay. So, but in fact, here's another argument. It is in fact possible to prove this statement in quantum information theory under two assumptions. Okay, the first assumption, both Alice and Bob can implement a constant depth quantum circuit on little o of L over G Newton qubits. What does little o mean? It means strictly less than. So if Alice and Bob are trying to perform a quantum operation on some qubits, some number of qubits, that scales sub-extensively in this semi-classical parameter, I want to say that they're able to do that. Why is that a natural conjecture? Well, remember, all of these statements are evaluated in this semi-classical limit as the ADS radius becomes much, much, much larger than Newton's constant. I would worry that if Alice and Bob tried to implement a quantum circuit on some number of qubits that scales as L over G Newton, well, each of those qubits is going to carry some constant energy. They're going to be trying to localize and act upon some number of qubits that localizes an amount of energy that is commensurate with the semi-classical parameter. They're going to cause back reaction. I'm no longer going to be able to trust my calculation. So this seems like a natural assumption. This constant depth quantum circuit is just that. I don't want to allow Alice and Bob to spend a very, very long time doing their operation because they're going to have some limited space-time region in which they're allowed to act. But say they're trying to do 3 unitaries, that should be possible. All right, this conjecture immediately connects us back with this family of tasks that I described before, for which we could prove that non-local implementation required some mutual information in a resource state. Right?
Why is the conjecture restricted to 2-dimensional quantum?
Great question. It's because of assumption 2, and we'll get to that in a second. Yeah. All right. So, good. What to say? All right. So, if this is true, and if we say, okay, Alice and Bob can do this task, and this kind of task in the bulk, then they can do this key n family of tasks for any number of qubits n that scales sub-extensively in the holographic parameter. Now our theorem was that non-local implementation of that task required a resource state with mutual information that scales as bigger than or equal to the number of qubits. Okay, so if Alice and Bob have to share a resource state with mutual information that is bigger than or equal to anything subleading in this parameter, they need to have mutual information that scales at least as this parameter. Right? Now, that might seem like a good argument, except that there's this second assumption, which is kind of subtle, which is that this theorem that I proved for you before used this kind of causal structure. And this is sort of getting to Edward's localization concern earlier. I can prove this theorem assuming that this is the sort of structure available to Alice and Bob, right? So I need to put in by hand the assumption that that's true. I need to put in by hand the assumption that the only meaningful resource that boundary observers could use to perform a task is the CFT state restricted to V1 union V2. This is a non-trivial assumption because, in fact, the CFT state restricted to V1 and V2 doesn't exist in isolation. It's some reduced density matrix that is entangled with the complementary regions, this diamond here and this diamond here. And those regions are in causal contact with the output points that are relevant for the task. So a priori, I can't tell you that there isn't some very clever protocol where, say, Alice starts with V1, she exploits the entanglement between V1 and this complementary region to teleport some information into that region. She then waits for that region to come out, that information to come out, and then she uses that somehow, right? So I just can't tell you that such a thing is not possible. I have to put that assumption in by hand. But if I put that assumption in by hand, then this theorem that I indicated to you earlier proves the conjecture. Now, Clay, as to your question about why I assume 2D QFT, I don't want to say, I'll tell you more about it afterwards just because we don't have that much time. I think that this assumption is much less well-founded above 2 boundary dimensions for reasons that I could explain. Furthermore, we have an independent geometry argument that fails above 2 boundary dimensions. So there's some sort of suggestive relationship between those things that means I don't want to say anything firm about what happens above 2 boundary dimensions.
But the presence of a singularity in the boundary correlator when the points are connected by a light like geodesic in the bulk, I mean that's a dimension independent thing. Can that
That's
be-
right, yeah, so maybe
Can that
one
be
thing to say about
reformulated?
that is that in global ADS4, for example, there are no such configurations. Right, so that's kind of special to 2 + 1 dimensions. If you want to, a thing I would really like to do is maybe make an explicit connection between twist operator 4-point functions in this result, in which case you might be able to get some mileage above 2 dimensions, but I think it would be tricky and very interesting. All right, so with the remaining time, I'm going to sketch for you an independent gravitational argument for the same exact conjecture that I just used before. So I gave you some quantum information reasoning for it. And now something pretty remarkable happens, which is that I can say, well, what if I try to ask the same question on the other side of the duality? Turns out there's a completely independent line of reasoning that brings you to the same result. So the thing we're going to need is this HRRT formula, the Hubeny-Rangamani-Ryu-Takayanagi formula for entanglement entropies of boundary states in terms of bulk geometric quantities. So there's very good reason to believe that in classical states, meaning ones with no bulk quantum matter, boundary entanglement entropies are computed by this HRRT formula. And this HRRT formula says that if I want to compute, say here's an asymptotically ADS3 spacetime, and I've picked some boundary region A, the entanglement entropy of the field theory restricted to that region A is given by the area of some codimension 2 extremal surface in the bulk that ends on the same points as A. So that's what this is sketching here. And this says, well, you look at all locally extremal surfaces with that property and you minimize over their area. All right. Immediately, there are plenty of problems you have to deal with. For example, these are areas of surfaces that go all the way out to infinity, so they are infinite. That's actually a good thing because entanglement entropies in quantum field theory are also infinite. But this isn't just a stupid inequality that tells you infinity equals infinity. There is, these equalities match meaningfully in regulations of the theory. I'm not going to go over this because I think it would just take us too far afield, but the idea is that if I introduce a regulator in my field theory which makes this finite, there's some corresponding regulator I can introduce in my gravity theory that makes this finite, and the regulator-dependent quantities match in an interesting and meaningful way. Okay, so there's plenty of evidence for this. There's a path integral argument, very famously due to these authors, that uses some formal manipulations of a gravitational path integral. There's, before that came this very interesting observation that the entanglement entropies defined this way satisfies some standard and highly non-trivial entropy inequalities. So it's true, for example, that in any quantum system, there's this inequality called strong subadditivity that all entanglement entropies need to satisfy. This formula satisfies that inequality. And it's a very non-trivial thing. So there's good evidence for this being a reasonable assumption to make. So the goal, and something that we did in our paper, is to take this QI conjecture in the previous slide, and because it's fundamentally a statement about entanglement entropies, we'll translate it into a geometric statement about the areas of extremal surfaces, and we'll try to prove it as a statement about how causality constrains the areas of certain extremal surfaces.
So what assumptions do you make about the bulk theory, like the bulk geometry? It satisfies the Einstein equations, or
I'm going to
something
assume it
else,
satisfies the null curvature condition, or equivalently Einstein's equations plus the null energy condition. And I'm going to put a global causality condition. Right, okay. So here's the null curvature condition, which I'll put in. And there's a global causality condition, which is the ADS equivalent of assuming that the spacetime has a Cauchy slice. Okay. So let me denote by gamma sub A this extremal surface corresponding to A, the boundary region A. Now I'm going to translate this mutual information statement into a statement about extremal surfaces. Well, the statement that the mutual information of 2 regions is non-zero, or is non-trivial at leading order in this semi-classical parameter, is exactly the statement that the union of the HRRT surface for V1 and the HRRT surface for V2 is not the same as the HRRT surface for the union of the 2 regions. So this is a topological statement about these extremal surfaces. So topologically, it sort of looks like this. Imagine that V1 and V2 are boundary regions. I'm drawing a space-time from a bird's eye view. If this mutual information is subleading in the holographic parameter, then I'll have this case where the extremal surface corresponding to the union of V1 and V2 is just some piece near V1 and some piece near V2. Whereas the case where the mutual information is extensive in this semi-classical parameter looks more like this. Okay. So what we're going to try to do is we're going to argue that when we have an arrangement of points with the kind of causal structure we were talking about before, the extremal surfaces are going to have to be in this configuration. Okay? We aren't able to prove it, but we are able to make some formal arguments that, up to some sort of non-rigorous assumptions, I think very strongly suggest that this is indeed the case. And that's why I've written proof in quotes by contradiction. So what we're going to do is we're going to use Aaron-Wall's max-min formula. Here's how this formula works. You assume the null curvature condition, which is that the Ricci tensor dotted into any null vector is non-negative. You also assume, I haven't written this down, there's this global causality condition called the ADS hyperbolicity. It's pretty hard to violate. It's sort of, the souped up version of there being no closed time-like curves. So what Aaron's max-min formula says or claims is that there exists a complete slice sigma on which this extremal surface, V1 union V2, is globally minimal in its homology class. If these words don't mean anything to you, ignore them. All right. So already there's a problem with making sense of this statement. It's not clear what I mean by a surface of infinite area being globally minimal. The crux of Aaron's max-min formula is that it makes sense for any regulation scheme in the theory. And in fact, it's provably true for any consistent way of regulating the areas. But it's not provably true that this statement remains sensible in the limit as you take the regulator to 0. So we're going to have to assume that all of the sort of formal manipulations that go into Aaron's max-min formula still work in the continuum limit. And our argument is going to require manipulations of that same kind, which is why it's not a proof, but I think it will still be pretty suggestive. So here's how this works. Assume towards contradiction that this surface has the disconnected topology, the one that looks like this. So now sigma is a maxi-min surface. It's this slice of the space-time on which this curve is supposed to be globally minimal. And what I'm going to do is I'm going to use this causal property of the space-time to construct a different surface on the same slice that has less area. Sorry, there's a missing A there, less area. And that surface gamma tilde is going to look like this. All right? So here's how this works. We'll do, I think, 2 more slides. All right, there are 2 tools. The first one is the focusing theorem, or rather a special case of the focusing theorem, which tells you the following. When you assume the null curvature condition, any null deformation of an extremal surface is area non-increasing. What does that mean? Take this green curve here, assume that's an extremal surface. It's locally extremal. Its area doesn't change under small compact variations at linear order. Right? Now I'm going to choose one of the orthogonal null directions to that surface, and I'm going to shoot off a light sheet in that direction. That's what this sort of green surface going up and to the right, coming out of this green curve, is supposed to represent. For those of you who think a lot about null geometry, what I really mean is the boundary of the future of a certain region. So this surface is made up of some null generators that are cut off at caustics or self-intersections. But if those words don't mean anything to you, it's okay. I just want you to take on faith that if I draw any cross-section of this surface away from the original cross-section, the area is going to have decreased. Or rather, it's not going to have increased. All right? So that's what this inequality is supposed to tell you. The sum of these 2 red cross-sectional areas is less than or equal to the original area. Okay. If this surface is related to this one by a compact deformation, then this statement is just true. I'm going to want to interpret it as being true even when I take, sort of uniform deformations of the entire surface that are not compactly supported. That's the kind of formal manipulation I'm talking about that we have to make some assumptions about sort of the consistency of. All right. The second thing we need is a version of Hawking's area theorem, which says that under this appropriate global assumption, this ADS hyperbolicity, null deformations along causal horizons are area, well, okay, let me just tell you what the picture is. Ignore this sentence. All right, pick a point at infinity and look at its past light cone in the bulk. This is like the event horizon of a black hole. You look at the set of all points at infinity and you look at their past light cone, okay? The area theorem tells you that as you move to the future along that null surface, cross-sectional areas increase. That's just Hawking's area theorem. And I've drawn it in pictures here. If I looked at two cross-sections of this light sheet, the one further in the past is going to have area less than or equal to the one further in the future. All right. So now we're ready to make the argument.
Can you say the non-rigor, the formal thing that you said in the first bullet point? You mentioned a kind of formal statement that you had some compactly supported statement. And
This statement makes sense if this deformation, if this surface is a compactly supported deformation of this one. Otherwise, what happens is that I'm sort of moving this surface all the way out at infinity, and I need to account for what happens in sort of the infinite area differences down there. And I haven't done this. I don't necessarily know how to do it consistently. There are some actually really intricate and interesting geometric problems in trying to do this that at the moment, I don't know how to resolve. So I just need to deal with a formal inequality, okay? Which again, because I'm assuming Aaron's maximin formula, like I'm making the same sort of non-rigorous set of assumptions as that formula, right? Okay, so again, we start with this green surface, which is on some maximin slice sigma, and we're trying to construct a different surface on that slice with the smaller area. So the first thing I'm going to do is I'm going to draw future directed light sheets emitting from these green curves. So I've drawn this from two perspectives, so hopefully it's clear. These red surfaces are light sheets that sort of form a tent in the future of the green curves. That's what this picture is supposed to represent. This is a tent that's towards us, coming out of the screen into the future of that maximin slice. And the question I ask is, well, I have two preferred points at infinity, R2 and R1, coming from the setup of my problem. Where do their past light cones intersect the light sheet? And the answer, and I will ask you to trust me on this, though I'll argue for it, this is something you can prove very carefully, is that the intersection of these light cones with this light sheet needs to look like this. So this black cone here represents the boundary of the past of R2. So everything south of this black line is strictly in the past of R2, and everything north of this black line is outside the past of R2. And this black line is the boundary of the future, or the boundary of the past of R1. So everything south of it is outside the past of R1, everything north of it is inside the past of R1. In particular, what that means is that this entire portion of the light sheet that lies in between the two black lines lies within the past of both R1 and R2. Now, it is this causal condition that guarantees I can draw a picture like this. Because basically what happens is that this causal condition that says there exists some non-trivial set of points that are in the future of C1, C2, and the past of R1 and R2. Well, all of these points along that seam basically have that property. All of these points lying on this seam in between these two black lines are in the past of both R1 and R2, and they're in the future of both C1 and C2. So it's this condition that lets me draw this picture and not have a picture where, for example, these two black lines intersect one another. All right? Okay. The paper has a very, very careful proof of this picture, but this is the most I can tell you for right now. So if you trust this picture, then what do you say? Well, by the focusing argument, this surface, which consists of the two black lines and two copies of the red seam running between them, is less than or equal to the area of the original surface. Why is that? Because if I go along this black line, and then I go along the red seam, and then I go along this black line, that's some cross-section of the light sheet that started at this green surface. And the other part of it is a cross-section of the light sheet that started at the other green surface. So by the focusing theorem, this needs to have area less than or equal to this. Now, when I throw away all of the points on the red seam, that's going to strictly decrease my area, because that's some space-like curve. So I end up concluding that the combined area of the two black curves is less than or equal to the combined area of the two green ones. Now, the amazing thing that happens here is that, remember, each of these curves was a cross-section of a past light cone coming from a point at infinity. So what I do this curve is a cross-section of the light cone coming from R2. This curve is a cross-section of the light cone coming from R1. I can deform those things into the past along those light cones, apply the area theorem, and I find that the area of those cross-sections is non-increasing. Okay? There are many things you need to be careful about in doing this. You need to make sure points don't hit the boundary. You need to make sure you don't hit singularities. It's all done in the paper. But if I assume that I can do this deformation all the way back to the maximum slice, then I end up constructing a curve that looks like this, a blue curve, that is area strictly less than the green one that I started with. Because I constructed it from the green one using area decreasing operations, or rather area non-increasing operations plus this strictly decreasing one of throwing away the red points. All right? This proves the theorem. I mean, if you accept that all of these formal manipulations are well-founded, then this just gives you the proof of the theorem by appealing to maximin. All right. There are many caveats, which I won't say because we're out of time. There are all sorts of things you need to deal with. For example, if your space-time has singularities, then your light sheets can look like this. You have to treat them carefully. This is all done in the paper. You know, these simplified pictures that I drew are not all of the possible cases. We spent months kind of like making sure that all of the possible cases were treated very carefully. But hopefully this is suggestive. And I think, I guess I should ask the organizers, should I wrap up now and go to questions? Should I do another 5 minutes? I don't know how long you usually go.
How much more time would you need?
5 minutes? It's fine. Is that okay? I don't want to, like, I really don't want to. Sure. Okay. Well, let me just tell you, everything I told you is in the original paper, the one from 2019. So let me just indicate to you what happens in the one from 2022, the one we put out a month ago. What we do is we generalize this same setup to a case where we have n inputs and n outputs. Now this gives us n diamonds, you know, these little causal diamonds near each of the input points. And as a result, we have a much richer causal structure. There are a much richer set of causal connections that can exist between these points, and a much richer entanglement structure, because we can try to say things about some n-partite entanglement shared between n regions. I think I'm not actually going to tell you what the theorem is in view of time, but I want to emphasize a few things. The first is that in this case, we have no QI theorem to guide us as to what the statement should be. In the 2-to-2 case, we had some results about 2-to-2 computations in QI and their non-local implementation. Nothing is really known about n-to-n computations and their non-local implementation. So we didn't even know what the statement should be. What we actually did was we generalized these geometric arguments that I just gave you in the previous slides and said, well, if I want to use the same techniques, what could I prove? And that led us to a very interesting set of causal conditions and entanglement conclusions. So for example, one thing you could prove, ignore this line, one thing you could prove is that if the bulk admits an all-to-all interaction, meaning a place where all n inputs can signal and meet and interact and then signal all n outputs, then you can prove a family of mutual information statements, which say that for any bipartition of the boundary regions into two sets, you're going to have large mutual information. Sort of amazingly, it turns out that this causal condition is stronger than you need. There's a weaker set of causal conditions that can give you the same answer. And that's, you know, all these slides I'm not going to talk about, but the thing I just want to emphasize to you is that by thinking about the geometric tools, we were able to come up with a quantum information theoretic conjecture that could be argued for using the tools of general relativity. And the thing that I think is really exciting or interesting about this work, yeah, Edward?
Can you prove them on the QI side?
Yes. You ask, well, up to the same sort of assumptions that we had to make, right? You can ask, well, in the QI side, we needed the existence of a family of tasks that had some certain information theoretic constraint given causal structure. Now you can ask, if I want to use the same reasoning, what quantum information theorems would I need? And there are, so that's what I've said here. You ask, what QI theorems would we need to argue for the n-to-n claim? Can we prove them? And the answer is yes. You can just write these statements down as conjectures in quantum information theory and prove them. And the two theorems are, you know, I indicated to you that in the bulk, there was some weak causal structure, some weak set of causal connections that could be used to prove the theorem. One thing you can prove in quantum information theory is that that weak set of causal conditions, which this is just some technical statement. This thing that says gamma connected, that's just some set of causal conditions. And we can actually prove that if you have that weak set of causal conditions, you can use it to perform any quantum operation with arbitrarily high accuracy without any pre-shared entanglement. And the other thing we can prove is analogous to this theorem, we can construct a family of tasks such that given the kind of causal structure that appears in this problem, we can prove the requirement of a resource state with certain kinds of structure. Okay, so these are just facts about information processing in spacetime. They are fundamental laws of nature about how information can and cannot be processed under causal restrictions. But they are things that I don't think we would have known to ask about or look for if we hadn't been using this gravitational reasoning from the first place. Okay, thank you very much for your attention. That's all I wanted to say.
If you start off with a maximum theorem with some, like the RT formula with some quantum connections, what does that tell you about the quantum information processing?
Oh, the formula with quantum corrections?
Yeah.
Right, okay. So I only talked about the classical case because it's much easier to talk about. But there are these conjectured generalizations of the HRT formula, this quantum extremal surface formula. And okay, if you have the extremal surface formula, then you have the null curvature condition, which gives you the focusing theorem, and you have the max-min formula, right? Okay, now let's assume something like the quantum extremal surface formula applies. Then, okay, first of all, that statement is a little bit harder to make sense of, but if we make sense of it and we trust the quantum extremal surface formula, then we would need a quantum focusing theorem and a quantum maximum. All right, these are things that have actually been talked about in other contexts. There's this quantum focusing conjecture for which there is some reasoning, and there's this quantum maximin conjecture for which there is some reasoning. If you believe both of those conjectures, and you believe that all of the reasoning holds together when you combine them, then the same exact argument will work in the case with semi-classical corrections. I didn't talk about it because I think it's a lot less well-founded, but it's talked about in the paper, and we do comment that all of the semi-classical arguments go through exactly the same way if you make further assumptions.
Do they tell you something more about like the subleading corrections to the asymptotics?
No, because the statement is always going to be whether or not there is a non-trivial mutual information at leading order. Or rather, the statement is always going to be about, if you like this terminology, the statement is always going to be about the entanglement wedge having this connected topology. And that's always the thing you're going to be able to prove. It's a broad geometric statement about the structure of the spacetime.
So you had this kind of all-to-all communication in the bulk that you derived this family of relations. You said the causality condition coming from the bulk was more powerful than you needed?
Yeah, okay, so the statement is, given n inputs and n outputs, it is true that if an all-to-all causal connection exists in the bulk, then you can use that to argue for a particular inequality in the Ryu-Takayanagi areas that gives you this information-theoretic condition. You can make that same argument without having an all-to-all connection in the bulk. What you need is something weaker, which is a sufficient set of two-to-all connections. So you imagine that there are n agents distributed at all of these input points, and you say, actually, it's not possible for them all to meet up at once and interact, but perhaps I can engineer it so that it's possible for pairs of them to meet up. So two of them can meet up, and a different two can meet up, and a different two can meet up. And it's a fact that a sufficient set of such interactions that doesn't necessarily imply a location where all of them can meet up at once is sufficient to prove this same, or to argue for this same conclusion.
So, I mean, do you think there might be a stronger statement, a stronger information-theoretic statement?
For when you have the all-to-all?
Yeah.
I don't know. I've thought about it. These things are very delicate, I mean, actually, no, I'm gonna say the answer is no.
Yeah.
And why do I think it's no? Because we proved this theorem that this kind of causal structure, this weaker set that I described, is sufficient to do an arbitrary quantum operation without pre-shared entanglement. So the reasoning might be, if I have an all-to-all interaction, I can use it to do a quantum operation. But I'm telling you, oh wait, there's actually some tricks you can use to do a quantum operation, an arbitrary quantum operation using a weaker set of causal conditions. There are tricks that don't require everyone to be able to meet up at once.
I see. And
All
now
right,
you're-
so I don't think I should be able to say,
Yeah, now you're
something
talking
stronger.
about using a quantum resource in the bulk, or you're,
no, well, there's actually still no quantum resource. So the simple example is this one. Suppose I have three agents, A1 and
I
A2.
see.
A1 and A2 can meet up here and then signal everything.
Right.
A2 and A3 can meet up here and then signal everything. The way this works is that the person at A2, they start with no pre-shared entanglement, but the person at A2 creates a bunch of entangled states and distributes them to these 2 points. Okay, and then these are 2 points that have some non-locally distributed entanglement resource that they can exploit to do a non-local computation. So it was never actually necessary that Alice, Bob, and Charlie all meet up at the same time, because Bob could create some entanglement resource that could be used at later steps of the computation.
So no further questions? Thanks, John, again.